Hey guys, it's Coach Sane here, and in this video we're going to be explaining how to program our motors using EV3 MicroPython. So there are two types of components we're going to use today. The first one is the medium motor, and we normally use medium motors to program our attachments, and the second one is large motors. Now we normally use large motors to make our robot move, and it consists of the drivetrain of the robot, so we can make it go straight forward, straight backwards, and complete turns. So all up, we're going to be using two medium motors and two large motors for our competition robot. This is pretty standard and this generally doesn't change. I have seen teams that use two medium motors to drive, and this can be efficient for creating really compact robots. However, the sizable difference isn't really statistically significant and it's not really shown up in the results of the competition. So you can experiment with these things. It is very good to learn and try to do different things, especially after you have a bit of experience. However, for now we're just going to be using two large motors and two medium motors. The large motors will be used to drive and the medium motors are to complete attachments. Okay, so let's head over to the computer and explain how to actually program our motors in EV3 MicroPython. Okay, so this is my desktop screen and I'm just going to navigate to Visual Studio Code as always. As explained in the previous video, this is the application we're going to use to run MicroPython on our EV3 device. And I'm just going to go over to the Mindstorms tab right there, and I'm going to create a new project. Before I do that, I will open up the user guide as always. It's important to always keep your user guide open, and I'll be referring to it in this video, and you should just in general have it because it's always good to see if you're making mistakes, or if you just need to know certain components and how to program them, then you can do that here. And I'll show you where all of the important parts in this documentation are. So let's go back to Visual Studio Code, and now I'll just create a new project, and you can name your project anything you want, just as long as it's representative of what you're actually programming. So I'm just going to type motors underscore movement. That's all I'm naming this. You can name it whatever you want. And I'm just going to save it. And we should see this screen pop up right here. Okay, and this doesn't seem like much. Once again, always to get to your programming environment, it's going to be main.py. You can pretty much ignore the VS Code and .git ignore. So, as the name suggests, just ignore it. You just hit main.py and you will be opening up into this section right here. Okay, and as always, I'll quickly do a brief overview of what we learned last lesson. So the first 8 lines, you can just forget about it because all it does is import all of the components you need to know. Thankfully, LEGO does this already for us, so we don't have to write it for every single project. So just ignore it, make sure you don't touch it. If you do touch things, then you will see different results and things won't work. So just leave it for now and always work under line 15 and onwards. Okay, so now I'm going to explain how to initialize your motors. So I briefly explained the concept of objects in the previous video. Now let's just say you have a component you want to use, for example the medium motor. First we have to initialize that medium motor before we can actually program things to it. And we initialize our medium motor by creating an object name. So you can see here the EV3 brick, as LEGO has already created for us, they've already initialized the EV3 brick. And this left hand side of the equation, you can name that whatever you want. So I can call that brick, but I'll leave it as EV3 for now. But the right hand side of the equation, that's a very specific class name. And if you want to know where this class name comes from, go back to your documentation and go under programmable hubs. And as you can see here, this class EV3 brick is exactly the same as this class EV3 brick. And that's essentially all you need to do to initialize a component. So as I mentioned, we're going to initialize our medium motor first. So to find your medium motor class, all you have to do is go to EV3 devices and scroll to motors. Luckily it's already here, and there's actually only one class that we need to initialize both our medium motor and our large motor. This motor here, that's an NXT motor. You can forget about that because we're going to be using EV3 today. So to initialize our motor, all we need to do is give it an object name followed by the class name motor and then specify the port. So let's go ahead and do that. So make sure your object names are representative of the component that you're actually programming. So because it's called medium motor, I'm going to type in medium underscore motor. Now this can be anything you want. If you're happy with MM, you can. However, when a stranger comes to your program, they might not really recognize MM as medium motor. So that's why I prefer to have medium motor. Just make sure your object names aren't too long because you will be typing it over and over again. And also make sure they're representative of what you're programming. Okay, so now we're going to do equals, and now we have to get the exact same class name as the documentation states. So motor with a capital M followed by OTOR, so I'll type that in now. And now we have to initialize what port our motor is in. And there's a very specific way we need to do this. And to find out this way, just hit port right here. And as you can see, the port in itself has a class, and then you just have to follow that class by the letter of the port. And the way we separate these things, for example, you don't just write capital P ORT followed by B. The way you go from a blue class to a gray description is with a dot. So to actually specify our port, we have to type in capital P ORT dot the letter that we have our port in. And I've got my media motor in port D. So just to explain that once again, one of the parameters that is essential to program our port in initialization is to specify which port it actually is. And as I mentioned, to do that, all you have to do is capital P ORT. As you can see, the pop-up already has it there. And then dot, and then whatever port your media motor actually is in. And for me, this is motor D. And that's essentially it. Now, if you go back to the documentation, there are other things you can program. For example, the positive direction and the gears. However, this isn't really necessary because we can just apply negatives and apply different powers to make our attachment work. So when you're doing a motor and you're initializing this motor, you only really need to specify the port. And if you don't specify the port, then you're going to run into trouble. So make sure you absolutely specify the port. Okay, so while we're here, I'm also going to specify my large motor, which I have actually two large motors on my robot today, because one large motor is going to be used for the left wheel and the other large motor is going to be used for the right wheel. So what I'm going to do is I'm going to create an object name again, and my left wheel, remember I'm calling it something that's representative of what I'm actually going to program, equals, and as I mentioned before, EV3 MicroPython actually doesn't distinguish between large motors and medium motors. You can initialize them with the same command, motor, but now you just have to put the port that your large motor or your left wheel actually is in. And for me, I've got my left wheel in port B, and now right wheel will be in port C. And it's a very good idea to have your ports as B and C. This is because LEGO Education actually encodes B and C to be calibrated together. And this calibration is essential for drive straight purposes. This is also important for turn purposes. So if you have your motors in A and D, it's a good idea to change it to B and C. This is for your large motors. Okay, so now that I've specified these three commands, we can now actually use these objects to do different things. So this initialization process, it's create your objects. However, I'm going to type here in the comment section, always good to write down your comment, initialization process. Hopefully I read it initialization right and process right, but we'll see how it goes. It doesn't really matter as long as you can understand it. Okay, and once again, a green comment has no effect on the robot. It's just for your benefit and to know what's actually going on. Also, if you have a stranger that comes and looks at the code, they'll know what's happening. So I've now initialized my medium motor, my left wheel, and my right wheel, and I'm ready to do some programming. So the first example I'm going to do is to make the medium motor run. So on my robot, I've got a little J on the medium motor. So when I actually turn the medium motor, that J is going to turn. And this is going to simulate how an attachment will work. So to actually make a motor turn, there's a very specific command you have to do. So if we go back into this motor tab here, you can see there's measuring, and if you want to measure the speed, angle, or just reset the angle, then you use these commands. If you want to stop, you use these commands, but to actually make the motor run, we're going to go under the action tab. And if you want to make it run at a constant speed, you can use this run command right here. The problem with this run command is essentially you cannot control the distance it runs in the same command. So you can only run the motor at a constant speed. This means it will just turn forever and ever and ever. So this isn't very useful to us. The same is with the run time. So you can put a speed and a time. However, in our experience, it's much better to specify a speed and then a given angle of rotation. And therefore, the motor will run to that angle. And just to explain what an angle of rotation actually means, let's just say this circle here simulates the medium motor of the inside. And if you were to turn it one rotation, that would mean 360 degrees. And if you want to turn it half a rotation, then you will do 180 degrees. If you want to do 90 degrees, then you will do something like that. So specifying a speed followed by a target angle is what we want to do. And if you scroll all the way down, you can see this command right here, run target, is what we're going to use. So this run target, you can specify a speed and a target angle. There's also other commands that we need to type in, but this isn't really necessary because this is the stop.hold and the wait equals true. And what this essentially does is it'll stop the motor to a braking stop. However, we'll learn how to do this later. So for now, you can just use this run target command. You can also use the run angle or run time command if you want. It's just up to your own preference. However, run target, they all do the same thing essentially. It's just what do you want to control the duration by, either time, distance in millimeters, or angle in degrees. So to actually make this work, we have to go back to EV3 or MicroPython, and we're going to actually be doing our programming under line 22 here. So this EV3.speaker.beep, I demonstrated this in the previous video, but we don't need this today, so we can delete that. And now to actually make this command work, you first have to choose an object to make the command run over. So because I want to make my medium motor turn, I just have to write this object name down. So I'm going to write medium underscore motor. As you can see, the popper already here. So if you hit enter, it'll go to the whole thing. And now that we have this object name, to actually make it work, you have to do dot followed by run target. As I explained before, the dot is there because we need to make the object first. So we have our class as the object in blue, and then to separate the object from the command, you do dot followed by the gray description. And make sure the gray description is exactly the same. We're also going to specify a speed in degrees per second and an angle in degrees. So that's run target, make sure it's exactly the same, and that looks good. So I'm now going to write 2000 and 250. So what is 2000? If we go back to the documentation, 2000 is actually the speed in degrees per second. Now this is completely up to you. I've found that just trying out different numbers and then seeing the result is the best way to go. You don't have to do any sort of maths using speed equals distance over time. However, if you want to be precise, you can. You may save more time just by trial and error. So I found that 2000 is a good speed to make an attachment run at. That's in degrees per second. And my target angle is going to be 250 degrees. So that target angle, if this is 0, to make it go 360, you would turn it 2 times just to make the Samsung logo come back. And then to make it 250, it'll just be a little bit less than that. So this is going to cause my J on the robot to go a little bit forward, but not completely forward to hit the robot again. So I'll explain that in the video. So let's see what this program actually looks like. Okay, so as you can see, all that did was explain what happened in the program. So the medium motor ran at 2000 degrees per second for 250 degrees. And generally speaking, this only makes one motor run. So if you want to make 2 motors run, then we're going to do something in the future. Now you might be thinking, alright, I've now made my medium motor run. What if I want to make my large motor on the wheel run? All you need to do then is just change this command. So I'm just going to delete this. And if you want to do a run target for your left wheel, all you have to do is type in your object name, which is left wheel, and then let it equal. And we're going to use the run target command again. So I'm going to do a run underscore target, open my brackets, and I'll do 3390. So what is going to happen if one motor isn't turning but the other motor is? So this is the same as one wheel being stationary and the other one moving forward. As you can imagine, this is going to be a one wheel turn where it's going to turn in the direction of rotation of that one wheel. We'll see what this looks like in the program, but just to explain my parameters here, I've got 3000 degrees per second, which is the speed. That's a little bit high, but we'll see what this looks like. And then 390 degrees to actually target a turn. Now this 3000 degrees per second, that might seem a little bit high. However, as we'll see, it's actually quite slow because we're only moving one motor at a time. Now, in the future, just in a couple of minutes, we'll explain how to make a 2-wheel turn. So a 1-wheel turn is where one wheel is moving forward and the other one is stationary. Now this is going to be a 1-wheel turn. To make a 2-wheel turn, what we're going to need to do is turn one wheel forward and one wheel backwards. This is going to be a turn on the spot, however, we'll get to that soon. So let's see what this looks like. Okay, so as you can see, that just did a simple turn. Now, in reality, we don't do turns like that too often. The only reason why we may do it is if we have an object that we don't want to get loose, because that is a small and quite an arduous turn. We can have a more mobile and compact turn with a 2-wheel turn. But in general, if you're ever running an attachment or one motor at a time, this run target command over your object name, that's going to be fine. So all you need to do is specify a speed and a target angle and it's all good. Okay, so I previously mentioned that often we need to do 2-wheel turns. And 2-wheel turns, as you can imagine, if one wheel is turning forward, the other one turning backwards, it's going to do a turn on the spot. And this turn is going to be much more efficient than the 1-wheel turn. Now, you might be thinking, okay, how do I run two wheels at the same time? And if you're thinking like a programmer, you may be thinking, okay, let me just copy paste this command. And instead of doing left wheel, I'll turn right wheel. But there is a problem with this program. So it's first going to turn the left wheel and then it's going to turn the right wheel. That's not really a two-wheel turn. It's just two separate one-wheel turns. That's why LEGO Education actually has a specific object name and a command to run two large motors at the same time. And it's actually got nothing to do with this run target command. All you need to do is delete this. And I'm going to go back to the documentation. And to run two wheels at the same time, this can be important for either going straight or for turning on the spot. You go down to this robotics tab here. And as you can see, this class called drive base, that's going to be your object name. So we have to create a new object that specifies the left motor, right motor, wheel diameter, and axle track. And this class is now going to let us do things like going straight by moving two motors at the same time and doing one wheel turn in place. So just to explain what these parameters are, you have to specify your left motor. This is going to be our left wheel, our right motor, our right wheel. We then have to do wheel diameter, which is simply the diameter of the wheels, and axle track, which is the distance between the points where both wheels touch the ground. So there are actually diagrams within this documentation that you can look at. However, you don't need to get these exactly specific. You can just use trial and error to get the right distance, but I have measured mine out and you should measure yours out too. So now this is a class, which means we need to create a different object. So your object name for this drive base will generally be robot. We can't call it EV3 because we already have EV3 as an object name. So my object name is going to be robot. And I'm going to let robot equal drive base. As you can see, the pop-up is already here. And now we just need to specify our left wheel and our right wheel. So our left wheel is in motor B. So instead of writing out this whole command right here, you can just write left wheel. And that will have that there, followed by a comma. And then you have to write right wheel, followed by a comma. And now all you do is write wheel underscore diameter. So diameter. And that's going to be, for me, 55.5 millimeters. And my axle track is going to equal 104 millimeters. And now you can see this is blue because this is a parameter that the drive base function automatically knows. So if we change this even a little bit, it's going to change and it's not going to work. So make sure you have all of these commands exactly the same as you see it here. This left motor and right motor, the reason why that's different is because I have my left motor called left wheel. So you have to specify exactly what your left wheel object name actually is. And for me, that's left wheel and right wheel. Okay, so why have we created this object? The reason is this robot drive base function is going to let us go straight, forward, back, and make turns very easily. So if we go back to the documentation and we go back to the robotics tab right here, this class drive base, if you go down, there are certain commands we can use. So if you do robot, which is the class name, dot straight, remember we always put a full stop or a dot to specify the difference between our object name and then the command that object name is going to do. So this robot.straight is going to drive straight for a given distance in millimeters and then stop. Likewise, robot.turn is going to turn for a specific angle. So let's just do an example with robot.turn and then we'll do an example with robot.straight. So now that I've got my drive base initialized, all we have to do is write our program and I'm just going to do robot.turn. And I'm going to open my brackets and let's go back to the documentation. As you can see, you just have to give a specific angle. So I'm going to do a 110 degree turn. So let's see what this looks like. As you can see, this was just a simple turn on the spot, and it was much more efficient and faster than the one wheel turn. This is why we're going to mainly be using robot.turn to actually turn. And as opposed to the run target command, this was a lot faster, and the run target command actually changed the position of the robot. The fact that this turns in its place means it is more mobile in a tight competition map. Okay, so the question might be, what if you want to turn the other way? And quite simply, instead of turning 110 degrees, which is this way, you will turn negative 110 degrees, which is the other way. So just put a negative in front or the minus. And let's run this and see what it looks like. So as you can see, it just did a turn the other way. So in general, if you ever want to do the opposite thing, you can just put a negative in front and that's just all going to help it go the opposite way. Okay, so now the important question. We know how to turn, we know how to move our medium motors, but to get from one spot to another, you're going to need to go straight, which is why if we go back to the documentation, you can see this straight description here is going to drive straight for a given distance in millimeters and then stop. So let's actually use this. once again, make sure you have your object name. So I'm going to delete this. Our object name is we're going to run it over a robot, which is the same as this one right here. And then we're going to do dot and then the grade description, which is straight and then a distance in millimeters. So let's write robot.straight, open our brackets, and I'm going to do a 250 millimeter straight. And that corresponds to a 25 centimeter straight. All you have to do is move the decimal place backwards once, and that will convert from millimeters to centimeters. It's much more intuitive to work in centimeters. However, the way EV3 MicroPython works is it's given in millimeters. So if you ever have any sort of arduous conversions that you need to make, all you need to do is either open up Google and you can go centimeters to millimeters, or you can do the maths in your head if you're confident. Okay, so let's see what this program looks like. Okay, so very simple, it just went straight forward. Now, as you can imagine, if you want to go backwards, all you need to do is put a negative here. Okay, so you might be thinking, alright, great, I know how to go straight, I know how to turn, I know how to move my medium motors. Am I done programming? And the answer is no, for two reasons. The first one is inaccuracies. So this robot.straight, as you can see, when it completed its 250 millimeters, it then stopped the motors. However, the motors didn't break in a sense. It actually just stopped them and there was gradual power, so it went a little bit over 250 millimeters. And the reason why we can see this is because it went a little bit further. So to actually make the robot stop at 250 millimeters, you need to apply a braking force. And there are 3 commands you need to memorize, and we're going to be using this over and over again, so you'll automatically memorize it. But these 3 commands are robot.stop, left motor, actually left wheel because I have my object name as left wheel, dot brake, so dot brake, and right wheel dot brake. Okay, these 3 commands right here, this is going to make the robot do a braking stop. So after it calculates 25 centimeters with its motor encoders, after it hits that, it's going to brake and it will do approximately 25 centimeters. That's the first problem we have with our programs right now, and we've just rectified it. Now that may only look like a marginal difference, however, errors add up over time. So for example, if you're doing one straight followed by another straight, and you go, well, the error the first time was about 1 centimeter, and the error the second time was about 3 centimeters. In total, that's 4 centimeters of error. And as you can imagine, if you're doing a lot of straights and turns, there's going to be a lot of errors that add up. We now need to find a way to minimize those errors. So another error that we have is with our turns. Our turns aren't based on the angle of the robot. In fact, our turn is based on the rotation of the wheels. So what I'm going to do to demonstrate this error is create a program that drives in a square. So to drive in a square, essentially all you need to do is drive straight for some distance and then turn 90 degrees. Drive straight for that same distance, turn 90 degrees, and so on and so forth until you have all 4 sides of the square. So I'm just going to write down this program. All we need to do is robot.straight followed by robot.turn, and I'm going to do 110 degrees. And now basically, I can just copy paste this command 3 more times because there are 4 sides to a robot. So Command C to copy and Command V to paste, that's for Mac. And so now it's going to go straight and then turn, straight and then another turn. So that's 2 sides completed, that's 3 sides, and that's 4 sides. And this is going to do a square that the robot has created. So let's see what this looks like. So as you can see, this essentially just did a square, but this square wasn't perfect, and the reason for this was because of inaccuracies. So the first inaccuracy was because there was no gradual stop to the motors. So we can rectify that by putting our 3 commands after every single straight. The second inaccuracy is actually very minimal and you can't see it. However, when we specified it to go straight, the robot actually didn't drive perfectly straight. This is because the robot can be an imbalance in the weight. This can also be because of wheel slippage that causes one wheel to turn a little bit more than the other, so the actual position of the straight is going to veer a little bit. We call this just in general veering. And to fix veering, we're going to use a gyro sensor in the future. Another problem with our program that caused inaccuracies is our robot.turn. As I mentioned previously, our robot.turn is based on motor rotation of the wheels as opposed to the absolute angle of the robot. So to fix this, we're going to use the gyro straight in future videos. So as you can imagine, to actually remove these inaccuracies, you need to use sensors and you need to learn how to program these sensors with these straights, and we're going to learn how to do that. Okay, so that pretty much wraps up this video. Hopefully you learned something, and this is just basic straights and turns. So essentially, this is the bare basics that you need to make your robot move. In future videos, we're going to be talking about how to minimize the inaccuracies that are caused by these bare basic programs by using sensors such as the gyro sensor, line follower, and all of these sorts of sensors and programs. So that wraps up this video. I guess I'll see you guys in the next one.